Hey kids, welcome to section 7.1 confidence intervals with sigma known. Today I'm going to teach you how to find the confidence interval for the mean when sigma is known and how to determine the minimum sample size for finding a confidence interval for the mean. So we're starting a chapter on confidence intervals today, and one of the aspects of inferential statistics is estimation. And that's the process of estimating the value of a parameter from information obtained from a sample. So, since the populations from which these values are obtained is large, these values are only estimates of the true parameters and are derived from data collected from samples. The statistical procedures for estimating a population mean, proportion, variance, and standard deviation is all of the different ones that we're going to talk about in this chapter. Suppose a college president wishes to estimate the average age of students attending classes this semester. Well, the president could select a random sample of 100 students, and find their average age of these students, say 22.3 years. From the sample mean, the president could then infer that the average age of all students is 22.3 years. This type of estimate is called a point estimate. A point estimate is when you use a sample value to estimate something for the population value. Now, these sample measures or statistics are used to estimate population measures or parameters. They're called estimators. And the sample mean is a better estimator of the population mean than the sample median or the sample mode, because a good estimator will have three properties. The first property is that the estimator should be an unbiased estimator. That is, the expected value or the mean of the estimates obtained from samples of a given size is equal to the parameter being estimated. It's an unbiased estimator. It's not skewed in any way by any of the data values. Two, the estimator should be consistent. For a consistent estimator, as sample size increases, the value of the estimator approaches the value of the parameter estimator. So basically, if we're using a sample mean to estimate population mean, then as the sample size increases, our sample mean will get closer to our population mean. And three, the estimator should be a relatively efficient estimator, meaning that it can be used to estimate a parameter and it has the smallest variance possible. So we're going to use these point estimates to make an interval estimate, and that's just a range of values that we're going to estimate for the parameter. So in an interval estimate, the parameter is specified as being between two values. So either the interval that we create contains the parameter or it doesn't. A degree of confidence, usually called a percent, must be assigned before an interval estimate is made. So, for instance, you may wish to be 95% confident that the interval contains the true population mean. Well, why 95%? Why not 99 or 99.5%? So, if you desire to be more confident, such as 99 or 99.5% confident, then you must make the interval larger. So, to be more confident that the interval contains the true population mean, you must make the interval wider. To make it wider means you go up in confidence levels. So, the confidence level is the probability that the estimate contains the parameter or doesn't. A confidence interval is that actual range of values that we're estimating for the population parameter. Three of the most common confidence intervals used are the 90%, 95%, and 99% confidence intervals. But you can be any percentage that you want to, those just happen to be the three most popular. So there are two assumptions when finding a confidence interval for a mean when sigma is known. The first one is that the sample is a random sample. That's pretty much standard now for everything we ever do. And number two, either the n has to be greater than or equal to 30, or the population has to be normally distributed when it's less than 30. So basically, just make sure your sample is a random sample and make sure it comes from a normally distributed population. Then we get into the formula, which is right here. You take the mean x bar, you subtract the critical value z alpha over 2, and then you multiply it by the population standard deviation divided by the square root of the sample size. Then to get the other half of the interval, you add instead of subtracting. So this x bar is called your sample mean. The z alpha over 2 is your critical level. It comes from the z table or inverse norming. And your z alpha over 2 times the standard deviation over the square root of n is called your margin of error. That's how much you're going to give yourself on either side of the mean when you're writing that confidence interval. The three most popular critical values for 90% is 1.65, for 95% is 1.96, and for 99% is 2.58. You can still find a critical value for any confidence level. These are just the most popular. Okay, so here's a graphic that kind of gives you an idea of what we're talking about. So if we're writing a 95% confidence interval, that means we're looking for the middle 95%, which means 5% is going to be on the outside of the confidence interval. Divide it by 2, and you have 2.5% on either side. Notice that the mean is here in the center, and then you have your margin of error on either side. There are two rounding rules for confidence intervals. If you're making a confidence interval for the population mean by using raw data, meaning like a list of numbers, you're going to round off to one more decimal place than the number of decimal places in the original data. We'll see an example of this in a minute. When you're computing a confidence interval for the population mean and you're using a sample mean, well, you're going to round off to the same number of decimal places as given for the mean. And again, we'll see an example of this in a minute. So let's see an example. Number of customers. A large department store found that it averages 362 customers per hour. Assume that the standard deviation is 29.6 and a random sample of 40 hours was used to determine the average. Find the 99% confidence interval of the population mean. All right, so the department store averages 362 customers an hour. So we have X bar equals 362. The standard deviation of the population is 29.6. The random sample is 40 hours. That's your N. And we're looking for the 99% confidence interval. So our Z alpha over 2 for 99% is 2.58. So then we go to write the confidence interval. We have X bar plus or minus the critical value times the population standard deviation over the square root of the sample size. So this is going to give me 362 plus or minus 2.58 times 29.6 over the square root of 40. So let's leave the 362 alone. Let's type in 2.58 times 29.6 over root 40. If I do this, I want to round to the same number of decimal places as the mean, which had no decimal places. So this is going to give me 12. So then my confidence interval is 362 minus 12, or 350 is less than the population mean, is less than 362 plus 12, which is 374. So we are 99% confident that the population mean customers per hour is between 350 and 374 people. So we sampled 40 hours. We found the average to be 362 customers. From that sample, we're going to infer to the entire population. And so we're going to say it's anywhere between 350 and 374. And that's with 99% confidence. All right, let's see another example. Credit union assets. So the following data represent a random sample of the assets in millions of dollars of 30 credit unions in southwestern Pennsylvania. Assume the population standard deviation is 14.405. Find the 90% confidence interval of the mean. Okay, so I know that my sample size is 30. I know that the population standard deviation, or sigma, is 14.405. I know that we're at a 90% confidence level, so Z alpha over 2, 90% is 1.65. The only thing I don't have is my sample mean. So I need to type these numbers into my calculator, and by putting them into L1, L2, and then I need to do one var stat in order to get the mean. The mean should have 3 decimals because the data had 2, and so that gives me 11.091. So my confidence interval is x bar, which is 11.091, plus or minus the critical value, 1.65, times the population standard deviation, 14.405, over the sample size, which is 30, so square root 30. So I leave the 11.091 alone. I type 1.65 times 14.405 over root 30 into my calculator. I need 3 decimals because it's one more than the data. So 4.339. So if I do 11.091 minus 4.339, I get 6.752 is less than the population mean, is less than, and then if I add the two numbers together, 15.430. So based on this sample of 30 credit unions, we are 90% confident that the population mean of the assets of credit unions is between 6.752 and 15.430 millions of dollars. We are 90% confident that the population mean of the assets of credit unions is between 6.752 and 15.430 millions of dollars. All right, so sample size determination is closely related to statistical estimation. How large a sample is necessary to make an accurate estimate? Well, the answer is not simple. It depends on 3 things: the margin of error, the population standard deviation, and the degree of confidence. So, for example, how close to the true mean do you want to be? 2 units, 5 units, etc. And how confident do you wish to be? 90, 95, 99%, etc. Well, for the purposes of this chapter, it will be assumed that the population standard deviation of the variables is known or has been estimated from a previous study. So we have a formula to calculate the minimum sample size needed for an interval estimate of the population mean. It's right here, n equals z alpha over 2, the critical value, times sigma, which is the population standard deviation, divided by the error, and then squared. And if necessary, round the answer up to obtain a whole number. So if there's any fraction or decimal portion in the answer, use the next whole number for sample size n. Always round up. Notice that when you're finding the sample size, the size of the population is irrelevant when the population is large or infinite, or when sampling is done with replacement. That's because the formula for determining sample size requires the use of the population standard deviation, not exactly how many people are actually in the population. So, a scientist wishes to estimate the average depth of a river. He wants to be 99% confident that the estimate is accurate within 2 feet. From a previous study, the standard of deviation of the depths measured was 4.33 feet. Find the sample size needed. Well, in the formula, you need to know the error, which is 2. You need to know the critical value, z alpha over 2. Well, for 99%, that's 2.58. And you need to know the population standard deviation, which is 4.33. So the formula says n equals the critical value z alpha over 2 times the population standard deviation divided by the error, and then you square it. So we have n equals 2.58 times 4.33 divided by 2, and then we square it. And we get 31.2. However, we need to say 32. Always round up. All right, let's take a look at an application problem. This one has to do with Kleenexes. Assume you work for Kimberly-Clark Corporation, the makers of Kleenex. The job you are presently working on requires you to decide how many Kleenexes are to be put in the new automobile glove compartment boxes. Complete the following. 1. How will you decide on a reasonable number of Kleenexes to put in the boxes? Well, there's lots of different ways that you could figure out how many Kleenexes should go in the box. One thing you could do is you could collect a random sample and ask them to keep track of how many Kleenexes they use. So we could ask a sample of people to keep track of how many Kleenexes they use. Kleenexes they use maybe in 2 weeks. Just get an idea. Again, lots of different answers. When do people usually need Kleenexes? Well, people need Kleenexes when they blow their nose. They usually blow their nose with a cold or allergies. Spell that right. Allergies. Or if they are sad. That's not as easy to pinpoint. Okay, number 3, what type of data collection technique would you use? Well, we should select some people with colds and have them keep track. So if we're trying to focus on people who have colds, then we need to go that way. So if focus is on people with colds, using Kleenex, then ask a sample of people with colds to keep track of Kleenex use. Now, it might be accurate, it might not be accurate, so that's something you'll have to think about when you examine the data. Okay, number 5, assume you found out that from your sample of 85 people, an average of about 57 Kleenexes are used throughout the duration of a cold, with a population standard deviation of 15. Use a confidence interval to help you decide how many Kleenexes will go in the boxes. Well, I need an N, which in this case is 85 for my sample size. I need an X bar, which is the sample mean, which in this case is 57. I need a population standard deviation sigma, that's 15. And it doesn't tell me what level of confidence we're going to use. And so 95% is the default. If they don't tell you what percent of confidence they are at, use 95. So Z alpha over 2, 95% is 1.96. So to actually write the confidence interval, I'm going to take the mean, which is 57, plus or minus the critical value, 1.96, times the population standard deviation 15 over the square root of the sample size, which is 85. We're using summary statistics, so we go to the same decimals as the mean. The mean has no decimals, so when I calculate 1.96 times 15 over the square root of 85, I want no decimals, I get 3. So 57 minus 3 is 54, is less than the mean, is less than 60. So we can say we are 95% confident that the population mean number of tissues of Kleenexes is between 54 and 60. All right, so explain how you decided how many Kleenexes will go in the box. Well, 60 seems to be the most reasonable. And if you notice, it's about 2 standard deviations above the mean, which means it's going to encompass a good majority of the people. So we can say 60 Kleenexes seems reasonable. Seems reasonable as it is almost 2 standard deviations above the mean. Certainly don't want to have 54 because then you might be missing out on some people. 60 is the high end, so that's going to cover the low end as well. All right, kids, that's the end of section 7.1. If you have any questions, please let me know. And as always, keep calm and keep trucking.